cool you down, I guess, was it? Use polymer concrete to cool you down.
For repair?
We had the same problem with the sluice gates, water coming in.
When was that done?
I guess it was done in 1975 something.
Okay, see this, since 83, the Bureau of Rec and Corps of Engineers have switched over to this technology. That would have been a preceding technology. Questions? Sure. Thanks, man. We talked about high strength and high rises and columns on bridges as one high performance concrete. In Seattle, all of the high rise buildings since 86, they used to be all steel, and since 86 on they're all concrete. And what they do in Seattle, I think, is pretty ingenious. I don't have any slides on it, but if you think of, that last slide we showed of reinforced concrete, this is what you typically see. Is that out of focus for you? No? Okay, it is for me. Typically you see the steel inside the concrete, inside the form, because concrete is good in compression, but not real good in tensile. Just the opposite, steel's real good in tensile, it's not real good in bending and flexural. So you combine those two properties together, you get a good column. What they've done in Seattle is, instead of putting the steel inside, they have hollow formwork, hollow tubes, round tubes, 8-foot diameter, no steel inside whatsoever, that go up through, well, you can see a couple of tire cranes here, that they literally pump the concrete into the bottom of these steel forms, fill up the steel form. There'll be one floor in height, and they put another one on top of it. So they'll be 8 to 12 feet high. They fill all the concrete up. The forms stay in place. So you've got this concrete column that's jacketed in steel. And you're going to put pressure on that concrete, and that's great, because the concrete's great in compression, but like a ball, if you press it, it wants to squeeze, and that's what happens when you break a cylinder. Did you ever break a concrete cylinder? Okay. When you squeeze a concrete cylinder, what happens is if it fails right, you've got a cone on top of a cone. You've got a cone on top of a frustrum. What happens is this part in between blows out like a rubber ball. When you squeeze it down, this stuff expands and blows out. Well, if you put a steel jacket around that cylinder, how much weight could you push on that before that concrete breaks? I don't know that it would. I don't know. But that's how they're building their buildings, and they're starting to do this in New York City now for obvious reasons. But they found that it's more economical. They don't have to deal with all the rebar. They don't have to deal with all that extra steel. These are stay-in-place forms. You put this form in, you fill it up with concrete, it stays there. You don't have to take it back out, move it around, put it in another place. It's like an assembly line. The buildings just keep going up. Every building that they've built in Seattle since that time has been built with this technology, with filling up the steel casings. I think that's a great way. Let's look at some high-performance concrete mix designs. Here's one that's used in piles in North Carolina. Everything, in their case, in the Carolinas, they're getting all their aggressive chemical attack from the brackish water. So everything that's underwater, the concrete piles underwater, from here all the way up to the bottom of the bridge deck is all high-performance silica fume concrete. That's where they're going to get their chemical attack. They don't get freeze-thaw. They don't throw any salt on the top here like you do, like we do up north. They get all theirs from down here. So from here, from underwater all the way up to underneath this girder here, from here on down, is all high-performance concrete. And this is the mix design that they used. 624 cement, some fly ash, class F, and silica fume. We're talking about these two being pozzolan materials, Yeah, sorry.
And they still have to worry about all the sand and the salt coming off the water from the winds, getting on top and eroding it.
Yeah, but I think on the roadway, they're depending on a washing action from rain to wash that off, where whatever hits this side here, and what would spray and hit this may not get washed off.
That'd be 365 days a year.
Yeah.
I mean,
yeah.
where we only put salt on for 3 months.
Yeah. Excellent point. Good point. That's what they do. In Florida, they stop about halfway up. They stop at 20 feet above the water. I mean, it's the same. Why? Every state's different, the way they do things. But that is a good point. I know in parking garages, if you follow the American Concrete Institute for Designing Concrete Parking Garages, they say anything within I think it's 1 kilometer or 2 kilometers of the ocean, you should treat it as if it was, you know, a parking garage here. It has the same salt attack. Well, what's the difference between a garage deck and a bridge deck? I mean, I'm supporting what you're saying. They should use it all if they're this close to the water. They do in the parking industry. Why don't you do it on bridges? I don't know. They're just slow in coming around. But in this case, in the Carolinas, they take it all the way up. In Florida, they actually stop here. They were looking for strength. In this case, besides low permeability, they were also looking for higher strength for load-bearing capabilities, so that's why they were pushing. This is typically twice as strong as what you would use if you were just looking for a lower permeable concrete. Here's one from New York DOT. Their actual mix, 500 pounds of cement, the same F-ash, some silica fume in there, and you see they're only making 5,000 psi. This permeability Coulomb number is a rating of the permeability of the concrete. A little bit different in mixes. You can see the goal, the difference in the water-cement ratio, lower for higher strength, more cement and silica fume for higher strength. If you're looking for permeability, you don't need strength. So you can take a lot of cement out. I've seen the lowest cement factor I've seen in Colorado. DOT actually has a high-performance mix design where they only use 390 pounds of cement per cubic yard, which if you go to Ferrier Brothers over here would probably blow their minds. They probably don't have a mix design over here that has less than 564 pounds of cement in any of their mixes. And they don't call it high performance, but yet in, you know, high performance, if you do it right, you mix the right materials together, you don't need that. And that's kind of the philosophy behind high performance concrete. Now that you've heard me talk for an hour or so, you all know high performance concrete philosophy. You all play poker and everything else. Tell me what that card is. Somebody.
Queen of Hearts.
Yeah, it's a Queen of Hearts. It's a Queen of Spades. I can't look at it either. I can say it without looking at it. If I look at it, I call it a heart too, but it's not. It's a Queen of Spades. And that's kind of what we're talking about with high performance concrete too. It's not the obvious. It actually means, if you use the technology, it actually means use the least amount of cement possible. Remember, we talked about the good actor and the bad actor in concrete. The aggregate's good, the mortar is bad. You want to use more aggregate and less mortar, but you want to make the mortar as good as you can possibly make it. Okay? So using cement alone only makes it a certain goodness, but if you add pozzolans to it, then you can convert more of that inefficient byproduct of cement water hydration into more cement. What you get is you get a particle packing if you're using silica fume and reduced permeability, ASR control with F-ash and silica fume. If you use less cement, you're able to use less water. And it's the amount of water in concrete that causes it to crack. You only need a certain amount of water in a yard of concrete to make concrete, roughly about 30 gallons of water. If you ever see any mix design that has more than 30 gallons of water per cubic yard, that extra water is only in there to make the concrete crack. And most people don't want their concrete to crack, so you don't need that extra water. So one way to control cracking is get rid of the water. Well, how do you get rid of the water? Get rid of the cement. We don't need all that cement in there anyhow, so everything is kind of following in line. Lower cement, lower heat of hydration. When cement and water reacts together, that produces the heat in the concrete. And if you have a differential temperature, like in those columns in New York, or in New York and Chicago, those columns, when they cast them, they may get up to 160 degrees temperature. If you have more than a 36-degree temperature difference between internal concrete and external, it'll crack, thermal shock, just because of that temperature difference. So what they do is they do two things. They try to make concrete that doesn't generate as much heat, And then they keep insulation blankets wrapped around those columns so that they can keep the heat in. It's only the shock of the outside coolness that will cause it to crack. And if you can keep it all warm and let it go up through its heat of hydration, come back to ambient temperatures in a week's time, you can take off those blankets and everything's fine. It's come back down to ambient temperature and you don't have that thermal shock anymore. But the idea of making concrete with low heat of hydration is good to help reduce cracking. Lower strength also helps to reduce cracking.
Talking about heating concrete, the hydration heat. They heat concrete and the precast gives wet concrete to cook it overnight.
Yes.
How would you reconcile the heating and non-heating argument? Here we want to keep the heating low, but in there they steam it.
In the case of the precast industry, they want to turn their forms every day. So you're working on a 24-hour schedule. If you're casting a beam, you know, the size of this, you want to cast it in a day, you want it to cook, and you want to be able to take it out of that beam and do the exact same thing tomorrow. And that beam has steel reinforcements and post-tensioning steel, and you're going to pull that steel and you're going to make a structural member out of this. The concrete has to achieve a certain strength before you can do all of those things. So the idea of heating in the precast yard is to try and get those, we said one of the characteristics you can do on high performance is get early age strengths. Precast would be that early age strength. They want 28-day strengths in one day so that they can turn that bed and make the same beam the next day, whether it's an I-beam or floors or something. But in the case of bridges or most other structures, it depends on the structure you're building. Heat of hydration comes into play when you're doing dams, big containment vessels, columns, where you've got big masses of concrete, feet thick. You know, in the case of some of the dams, the Hoover Dam is what, 60 feet, 200 feet thick at the base, something some ungodly like that. I mean, it's just an amount of thickness. Well, it's that mass of concrete that holds in the heat. When they built the Hoover Dam, you guys have probably seen the video on the Discovery Channel, they actually had pipes, copper pipes running through the formwork that they actually pumped chilled water through, ice water, through the pipes. They poured the concrete on top of all these pipes. The pipes are still in place. They poured all these concrete on there. As the concrete gets hard, as the cement water hydrates, it's a chemical reaction. Most chemical reactions do something. They give off a gas or heat or something. Cement water happens to give off heat. Well, if it's surrounded by all this other concrete, it's a great insulation. That stuff gets really, really hot. And if it gets too hot, then it can crack. You don't want cracks in a dam. You know, it's to keep the water back, not to let it come through slowly. So they actually ran pipes through the mass concrete and ran cool water through it to try and control heat of hydration. That was way before, you know, this type of technology, but it's still done. Chilled water through concrete and mass structures, dams, Bureau Rec does quite a bit of that.